All right. Now there's an alternative way for solving this problem. Once you get tau, you change tau into Vc. At that moment you get C1, that's a constant, the first constant. You can go on, integrate Vc, you get another constant C2. Okay? If you do that, you need two boundary conditions. These two boundary conditions will be used right away without using lambda. So you don't need lambda, actually. But anyway, in the textbook, they say it like this. I just want to follow them. Okay? Now, if you look into velocity profile, once you solve for lambda, you know the lambda there, here. And this lambda is not simply k plus 1 over 2. So it is not located right in the center here. So it means the maximum velocity is somewhere that is not center. So you have velocity profile looking like this. The maximum here is lambda r. Okay? Or if I write it a little bit more, maybe something like this. Actually, no. Okay? The left hand side of this maximum and the right hand side of maximum will not be symmetry. Right? But this part and that part will be symmetry to each other. So that's velocity profile, Vc. At the position where the velocity is maximum, if you plot shear stress profile, you will get something like this. This is tau Rz, okay? Tau Rz will become positive at this region. It will become negative in this region. What does it mean when tau Rz is negative? Here is positive, here will be negative. Does it mean anything? Does it get weird to you? If you look, tau itself supposed to be tensor. So tensor is supposed to have two directions. One direction would go along direction of velocity. So we have tau Rz. So one direction should point in z axis. Okay? The other one would point in r axis. We know that for z momentum should go in plus z direction always. Why? Simply because our velocity would go in plus z direction in any position. Okay? But our component here is a component of momentum transfer. Momentum transfer takes place from high velocity to low velocity. So from this region, maximum velocity is located there. So it will be transferred in this direction, going from high velocity to lower velocity. Okay? So tau RC in this region here would have direction like this. This one is positive Z. This direction is positive R because it goes from center toward outside. That's positive R. Positive and positive here makes the tensor to be positive. So that's why you get positive tensor in this region. On the other hand, inside there, even though direction of the momentum itself goes along plus Z direction, but direction of momentum transport go from maximum toward lower velocity. It's go in that direction. Okay? So our tensor would look like this. Here is positive C, here is negative R because it's pointing toward the center. One is positive, one is negative, makes the whole tensor to be negative. Okay? If you look from the top, now suppose this line is located with lambda r from the center. So this dotted line represents position where we have maximum velocity. Maximum velocity is pointing outward. Okay? So concerning direction of the momentum transport, from maximum toward inside here, momentum transport going inward. Okay? From the maximum going outward, the transport looks like this. So after you derive the whole thing, please notice the sign as well. If the sign looks like this, I would expect you to know the meaning. Okay? Wait a minute. All right? Any question? Yes?
We can write our velocity profile by using the equation we got.
Yes, you can. We have velocity profile, right? Right here. In this equation, R is only the variable. The rest is constant. If you plug R, one value, you get one value of VC. Then you can just use any program to plot the profile. But if you look roughly, you see that although there are logarithm of R, logarithm of inverse R, but R still square. This is dominating. So the profile is supposed to have the inflection point, have maximum point. But the curve is not parabolic because of this term. All right? So if there is no other questions, we finish chapter 2. Okay? Next step, chapter 3. All right, before going into chapter 3, I'd like to introduce some mathematical notations. First of all, partial derivative. We all know partial derivative. Okay? Suppose I am interested in concentration of some certain species in the fluid. And I want to observe this term, concentration change with respect to t, with respect to time. That means if I write it this way, it means that differentiation takes place when x, y, and z would be assumed to be constant, because it is partial differential with respect to t only, right? By definition of partial differential equation, you need to keep everything else constant. All right? So by this writing here, what does it mean? It means that you look for the change in concentration with respect to time at fixed position. Right? Because x, y, and z represent positions. So if x, y, and z were kept constant, that means you're looking for the change in concentration at fixed position. So it looks something like this. Suppose you have a river flowing in this direction perhaps. If upstream someone pour some red dye or red paint into the water, the paint here would flow along the current. Right. At the same time, the paint would disperse. Okay? If you have a bridge, let's say there's an observer sitting on the bridge or standing on the bridge, and then if he looks at this position only, you look at fixed position, what would you see? When someone pour paint down there, there's a painting pouring here. So along the way, the paint would go along the flow, and you definitely see at some certain period. After certain time has passed, you see no color at all, right? Because it's already passed. This change with respect to time is represented by this partial differential. Okay?